Hello and welcome to Kaggle, New York City.
Hey!
My name is Ervin. My name is Jared Moreno. This is the Kaggle, New York City user group meetup. We're not affiliated with Kaggle proper, so not Alphabet. So tonight's topic is the evolution of Apache Spark and the big data ecosystem. So it's like a primer on Spark. It's a very popular technology. First, we're going to give thanks to our sponsors. A little bit of background on why you should sponsor Kaggle New York City. So we'll plug you in your service. It exposes you to developers in New York City. You get mentioned at our events like this. You get mentioned on the YouTube channel, so this gets recorded and put on YouTube for the whole world. And the sponsorship is for us to just cover the organizational costs. So meetup is not free, and the website is not free. This month's sponsor is Lit. It's an events app. They are currently seeking interns for Django development, React Native development, marketing. You can email hello@getlit.app, and to learn more about the company, it's getlit.app. That's the domain. So, be social. Please subscribe to the YouTube channel Kaggle NYC and turn on the notification button. And we have a Twitter, so you can follow at Kaggle NYC for updates. If you don't see them on the meetup, sometimes you don't. We also have a study group. We call it the Machine Learning Study Group. It's on Sundays, 2 to 6 in Tribeca. So that's on the meetup page. We're always looking for speakers. So we have a couple of speakers lined up for March. Something on time series and something on NLP. We are currently looking for someone for February and beyond. So March. We're looking for April speakers, if anybody wants to speak. Why would you want to speak? To share your knowledge. You get a video on YouTube. Good self-imposed deadline. It's really good. Anything data or tech related is kind of on topic. SQL, Python, Cloud. And so a little bit about our speaker. Their name is Gary Cheung. Gary and I actually met working at Capsule Pharmacy, and Gary was the first sort of data engineering hire there, so he sort of set the tone, cleaning up the data situation at that company, and setting that up. He's since moved on to doing more consulting, and he told me that he can't really talk too much about it, so maybe he'll say what he can. And that's it.
Okay, cool. Hi everyone, I'm Gary. So we're going to talk today about the evolution of Spark and big data. So to give a little bit about my background, I started with a bachelor's of biology at Temple, went to Penn for a master's in computational biology. I started my career at Barclays as a tech analyst in the big data team. Then I worked for Live Intent, an ad tech company where I was a data engineer, then Cigna as a senior architect in big data. Then at Capsule as the first data engineer hire. Then at Caserta as an analytics consultant, and currently at an insurance startup that asked me not to talk about them, so I just left it blank. So today we're going to talk about 5 different areas. The history of big data, a quick intro to Hadoop. From there we go into Spark, how we transition to the cloud, and what's next. To make it easier, I have candy, 6 candy bars for random questions throughout the session, and a Q&A session at the end of every single session. So should we just dive right in?
Yeah, you're good.
Cool. So what is big data? It's actually a made-up term. O'Reilly coined it in 2005, just as a buzzword. It's overly used. No one really understands what it means. It's kind of a cliche term, but the formal definition for it is fast, big, and unstructured. So fast means that the data comes in at real time, usually streaming data. Big means that it's at the terabyte to petabyte scale. And unstructured means that it doesn't follow a row-com format. So that means JSON data, freeform text, videos, and etc. So give a really crude example of how something goes from small data to big data. If you took every trade in New York Stock Exchange for an hour, that might be about a gigabyte of data. But if someone asks for the 30 years of data for New York Stock Exchange, that might blow up to about 62.4 terabytes if you consider that that's 62,000 hours. Big data is not always better data. So data operates best when you vertically scale a system. You don't want to put small data solutions into a big data system. I've seen people try to put megabytes of data onto Spark. It just doesn't work. It's not meant for that. You really want to make sure that you're using the right tool when you're trying to solve for big data problems. To kind of talk through a little more about why, this is a ranking of different types of processes and what's fastest and slowest. So the fastest type of processing is actually L1, L2 cache memory inside a CPU. From there you go into actual physical memory. And then from there, disk, SSD drive, and then hard drives and network transfer. Actually, network transfer within a data center is is faster than hard drive access. But you want to try to keep most of your processing within these two categories, cache memory, memory, SSD. When you're moving off to network transfer within the data center, it slows down your processing tremendously. So kind of a quick history of how big data came about. The first data center was about a megabyte. It was created in 1965 by IBM. And then from there, the first supercomputer happened in 1975, could store about 4.7 gigabytes of data. And in 1997, that improved to 1.5 terabytes. From there, Teradata was released in 1999. It could store about 130 terabytes of data. It was the largest database at its time. In 2006, Amazon Web Services was publicly launched. In 2008, Yahoo released the first petabyte scale database, which stored 2 petabytes of data. In 2011, Hadoop was released. In 2014, Spark was released. And now in 2019 to 2020, you could hypothetically store infinite amount of data, but about the petabyte scale is where we're currently at right now. This is kind of a chart to show data capacity, and as you can see, it's just like flat line, and in 2008 just goes straight up because our scale has gone up tremendously, especially in the last 5 years. So this is an example of vertical scaling versus horizontal scaling. So when we talk about vertical scaling, we're talking about taking a machine and then adding more memory to the machine, or adding more disk or physical memory. So you're going from 1 CPU to 4 CPUs, and 1 gigabyte of RAM to 4 gigabytes of RAM. When we horizontally scale, we're actually adding more machines and connecting them together. So going from 1 server to 2 servers to 4 servers. When we talk about big data, we're talking about distributed computing most of the time. And in that case, there's usually a master node, worker node, master-slave relationship. So the master node is required because something has to coordinate most of the jobs. And the worker nodes are the ones that does most of the processing. But when you have a distributed computing systems, it creates a lot of problems. If you have data stored in multiple servers, how do you coordinate this data? What happens if a server goes down? How do you split up jobs that require shared data? And what happens when a job fails? In distributed computing, there are a couple answers to these questions. The master-slave relationship allows the workers to make sure they're coordinated, to make sure that the workers know what jobs they have to run. There's usually high availability, which is if one system fails, you have another system backup to take its place. And you have fault tolerance. You allow jobs to fail and you handle for it because you know that jobs are going to fail. And then you have monitoring to make sure the servers stay up. So before Hadoop, in around 2000 to 2010, there were a few solutions for what was considered big data at the time. You could store in an Oracle database. You could store data in Teradata, which was a petabyte scale database system, which was distributed but very expensive. You could create your own distributed messaging system using Celery and pass messages between nodes. Or you could use a high performance computing cluster. And that's actually where I started working with big data. It was back in grad school, undergrad at Temple University. I was processing human genomics data, which was about 3 gigabytes in size. It's not terribly large, but big enough you can't process it on a laptop. So we would have to use supercomputers with about 32 to 64 CPUs to process the data set. When we talk about big data, to kind of help frame the discussion, we need to talk about the phases of data processing. So we look at data processing. It starts with batch data feeds and data streams. From there, this data gets stored in the unstructured data storage, and then you do transformations on it to get it to a structured format where it's row columnar. You do further transformations for joins, aggregation, selects, and finally, this data can be analyzed and for machine learning purposes or analytics. So in the pre-Hadoop world, there were tools to kind of answer all these questions. For data streaming, there was RabbitMQ or IBM ActiveMQ. For batch load, there were ETL tools that had user interfaces, such as Informatica, IBM DataStage, or Microsoft SSIS. You could store data in a Unix disk storage or a RAID drive. You do structured data transformations directly in those ETL tools as well. Or you store the structured data in Teradata, Oracle, Postgres, and you can do machine learning using scikit-learn or R. So that kind of wraps up the first session. I kind of read it very quickly, but we'll open this up for Q&A for the first session. Anyone has any questions?
Scikit-learn existed well before 2005?
I'm not sure exactly when scikit-learn came out.
I think it came out after.
Yeah, this was for, I think, 2000 to 2010, the period before Hadoop.
Well, Hadoop started in 2007, 2008.
Right, but this was like covering like how would pre-big data, what are the non-distributed machine learning packages and so forth. Okay, we'll just go right into Hadoop. So Hadoop started in 2003 with a paper that Google released on the Google file storage system. And then in 2004, Google released another paper on MapReduce. These are the foundational papers that kind of inspired the Hadoop project. In 2006, Apache released Hadoop as an open source solution officially. Hadoop is a completely made up name. The creators of Hadoop named it after their kid's imaginary pet elephant. In a nutshell, it's an open source distributed processing system. So what are the components of Hadoop? So the base components of Hadoop are the resource management system called Yarn, a distributed storage system called HDFS or Hadoop Distributed File System, and then the MapReduce algorithm. The resource management system makes sure that it coordinates the distributed management jobs to ensure that the jobs go to the correct nodes and that jobs run correctly. I'll go into that a little bit more later. The Hadoop distributed file system allows you to store data across multiple servers. And the MapReduce algorithm is the algorithm that underlines every single Hadoop job. It's a functional algorithm that allows you to run jobs without sharing state by either a map function or a reduce function. So the Yarn Resource Manager has a couple components. On the master node of the Yarn Resource Manager is the actual resource manager itself, which is has two functions: a scheduler and application manager. The application manager coordinates with the node manager, which sits on each worker node, to understand how many resources are available for each node. So how many CPUs are available, what is the RAM, and so forth. The job scheduler is responsible for scheduling the actual underlying job. So when you submit a job into Yarn, the resource manager spins up an application master, which then spins up containers, and the actual application master is responsible for coordinating the underlying job. This is actually very ingenious because before it was a job tracker that was the central coordinator for all individual jobs. So now when you run a Hadoop job, the application master is responsible for running the job. So it takes a lot of the workload off of the resource manager for running the jobs. The Hadoop distributed file system is another system that Hadoop has that uses a lot of distributed computing concepts to solve some of the problems that distributed computing has. For instance, it has a master-slave relationship with a master name node and various data nodes underneath of it. It has high availability. So usually with your name node, you have a standby name node with a direct copy of the name node data if the name node goes down. It has fault tolerance by replicating data multiple times across each data node, and has monitoring using Apache Zookeeper. So Zookeeper is a project based out of Hadoop that kind of mimics the Unix file system, but it keeps track of the metadata across each of the Hadoop applications. Every application in Hadoop is named usually after an animal. Since they started with an elephant, everything else kind of just followed the theme. And this is a view of the HDFS architecture with the name node and the various data nodes. Each green block here is the actual block of data that's stored. And the name node is your master node, is the master node that coordinates the metadata across each of these individual data nodes. And here, there's 3 data nodes stored on one rack in a data center, and there's 2 other data nodes stored in another rack of the data center. So why did Hadoop become popular? For a few reasons. It was open source, so it had a community support underneath it. It was constantly being built up. It allowed you to use commodity servers. So the alternative at the time was Teradata, which charged about $30,000 per terabyte of data per year. You can get a cheap server for about $5,000 at a time to store about a terabyte of data at a one-time cost. It's a lot much cheaper and it doesn't require a license for Teradata or Netezza. And the main thing is it supports unstructured data processing. You couldn't do that with Teradata. You only could process data in row column format using SQL when you use Teradata. So when I worked at Barclays, I was actually on the first team that started Hadoop, and we started out with the Hortonworks open source distribution. So at the time, we were trying to process 30 years of historical trading, risk and analytics trading transactions, and we were trying to process our Oracle database. So the job would never finish. We would run it for multiple days, and it would just stall. So my boss decided to spin up Hortonworks, got a few servers together, and run the job in Hortonworks using Hadoop with Hive. And we were able to finish running the job within a few hours. From there, we moved from Hortonworks to an enterprise cloud era solution, and now that team is the main Hadoop ecosystem for the entire bank. So it kind of started as a side project out of the blue. There's a couple other projects within Hadoop, such as Apache Hive, which lets you use SQL and view your data in a row columnar format similar to a database. There's Apache HBase, which is based off of Google Big Tables and lets you store and query data in a key value format. So it's kind of like a massive big data cache. And Apache Pig, which is a functional language so that you don't actually have to write MapReduce to program it in the Hadoop ecosystem. It abstracts away some of the programming syntaxes for you. And so when we were looking at the data processing steps before, this is a comparison of all the different tools you would use in the Hadoop ecosystem to accomplish each of the steps in the data processing flow that you would want to do. So you could stream data using a project at the time called Storm. You could load data using Scoop. Data transformations can be done in Pig or MapReduce. You would store data on the Hadoop Distributed File System, or HDFS. You could structure and store your structured data using Hive, and then you could do machine learning on a project called Mahout, which ironically means man riding on top of an elephant in Hindi. So I'll stop there for Q&A. Yes?
How big was the world change when this came out? Did it get picked up and then everybody turned their head? Or did it have to take some time to get traction?
With Hadoop?
Yeah.
I think it was a big buzz at the time. People didn't really understand what it could do or not do, but it was really hyped up when it first came out. I think people were really excited by it.
So it was user pushed or was it developer pushed?
How so?
So was there the uptake? It was a lot of end users like the bank that were, this is amazing, we need more of this. Or were, because it started as a developer white paper project, was it, who pushed it forward after it was released into the wild? Was it more developers using it? Or did they find so many end users for it that it got dragged forward by that?
I'm not sure exactly. I mean, I think...
I can answer.
Sure.
No.
You couldn't do it yourself, so to speak, because you needed a cluster, like physical cluster. Usually, you know, people out of the blue don't buy like five boxes to form the cluster. So it still was happening within controlled environment. But the big push was Hive, actually. Because Hive, you could program in regular SQL, and it scaled beyond relational databases. And even to this day, most of the use of Hadoop is going through Hive or some variants of that. So this is truly became possible to run SQL queries of arbitrary complexity on terabytes or tens or hundreds of terabytes, you know, scale, and get predictable result within predictable time. So something that was impossible with relational databases, but using the same kind of tools. This was the...
Yeah, to kind of add on to that, the problem at the time was MapReduce is really hard to write. To break a problem down to a MapReduce problem, you have to think about it either as a map function or a reduce function. And a map function is like, it's one-to-one. So you have an input variable, and you have the corresponding output variable. When you have Hive, a lot of people who were traditional database programmers who didn't do more functional programming or even programming in general could just use SQL on top of Hadoop and do the transformations. So that definitely garnered a lot of adoption. I have a few questions for you guys, if you guys can answer for Candy. What is the default HDFS replication out of the box? Yes.
Isn't it 3?
Yes. Skittles, Hershey, or Almond Joy?
I'll take the Almond Joy.
Cool. And which language is Hadoop written in? Okay, well, I guess kind of killed it. Okay. What is the default HDFS block size for Hadoop 2.0? Guess, anybody?
128 megabytes?
Okay. 128 is correct. It used to be 64, they shifted it the second version. Okay, so I'll just start with Apache Spark then. So Spark was created as a research project out of UC Berkeley. It was released in 2014, and it borrows a lot of the same concepts as Hadoop, but it has one major shift, which is the resilient distributed data store. The RDD really is basically an object that's stored in memory. And that was a major shift between Hadoop and Spark, was that Hadoop does a lot of the operations on disk, and Spark uses in-memory processing whenever possible. When we look at the PageRank algorithm, you see here that Spark performed a lot better in Hadoop in running this benchmark test. Actually, more than half the time to run a basic Spark command. And then when you have control partitioning, where you are properly storing each data set in a control format on the nodes that you want, you get even better performance using Spark. So Spark actually doesn't require Hadoop to run. Spark can run by itself. When you run a Spark job, you create a driver program that creates a Spark context, which communicates with the master node, and each of the various worker slave nodes would have an executor or container to run the job, and each job is run into separate tasks. Another major value of Spark is lazy evaluation. So before a Spark job runs, it actually creates a directed acyclic graph to coordinate what is the best flow of functions and how to distribute the data to run the job so you get the best performance. And so actually most Spark functions for RDDs are broken up into two categories: a transformation or an action. A transformation is a function where one RDD produces another RDD. This could be a join, a group by keys, etc. And then a Spark action is an action where the data is actually returned back to the driver. So this is when you want to save it to a CSV, when you hit a collect command, which returns back the data to the UI, a take command to get like ahead of the top 10 elements, and so forth.
You got a question?
Sure.
What's an RDD?
Resilient distributed data store. It's the basis for it's a basis data structure for Spark.
Like a data frame?
No, we'll go into that in a second. So what happens is that when you write Spark, you have multiple transformations, and then we hit an actual action such as save to text. That is when Spark actually evaluates and starts to run through each of the functions up to that action command, and will create a directed acyclic graph, which is a flow of various functions to get to your final outcome. So there's various components of Spark. There's the RDD, which is the resilient distributed data frame. The operations with Spark RDDs are very similar to MapReduce operations in Spark. And then there is Spark data frames. This was released afterwards in a later version of Spark. A Spark data frame is very similar to a Pandas data frame. It treats data in a row columnar format, and even lets you write SQL commands to query and process your Spark data. There's Spark Streaming, which is the solution for streaming data into Spark. Spark doesn't actually have a real-time stream. It uses micro batches when it processes streaming data, which are basically batches but a very small quantity of data. It's still very performant, but it won't work for real-time streaming solutions. And then Spark ML is Spark's package for handling machine learning. It has statistics, collaborative filtering, clustering, and various data science pipelines built into it. And then finally Spark R, which is a light version of R on top of Spark. I will say Spark ML and Spark R are not as full-featured as scikit-learn or actual R itself. If we go back to the whole data processing pipeline, Spark has a solution for each of these. For data streaming, there's Spark Streaming. For batch loading, you can load directly into RDDs. You can store data, you transform structured data as data frames, store data on HDFS or S3. You can do transformations on Spark data frames. You can then do structured data storage on HDFS or Hive or even a cloud database, and then you do machine learning on Spark ML. The thing is, for storage, Spark doesn't handle that piece. You would still have to use HDFS or your local server or Amazon S3. But for all the other processing steps, there is a package inside of Spark for handling each of those steps. I'll stop here for questions. Yes?
Let me just explain what is RDD and data frame. There's a difference between Pandas data frame and real data frame, and Spark data frames, real data frame. The Pandas data frames are existing in the memory of one machine. these data frames existing on the whole cluster. So that means that they are broken into inside memory representations on many different machines. And Spark itself, the same way as MapReduce itself, knows how to get pieces of that and how to do the executions on those pieces of data that resides in the memory. So don't think that these data frames are the same. They are completely different pieces, and only there is a central mechanism which knows which piece corresponds to what place inside a much more gigantic data set that you can operate on. Okay?
Thank you. What was the other question?
Which one would be faster, a Spark RDD or Spark data frame, or is there no sweet compatibility?
Technically, Spark data frames translate down to Spark RDD, and they're optimized. So hypothetically speaking, it's a Spark data frame, but it's a very subjective question because you can write your RDD in a very efficient way. So it really depends on what kind of problem you're trying to solve. The Spark data frames are highly efficient.
Well, the data frame is RDD plus metadata that explains what exactly in that RDD is there. So RDD is just a block of data, and you can interpret it any way you want. The data frame added the metadata that will say, hey, first 4 bytes is an integer, next 8 bytes is a float, next whatever it is string, or whatever it is. So when you're writing SQL, for example, the system can know how to go and get your rows, not just the whole row, but only like piece of the row in one set. And that's where the efficiencies of SQL, implementation of operations on data frames are. So Spark at some point, created the whole API on RDDs, but then they saw that it's not that efficient, and they were competing against other implementation of SQL-based tools like Apache View, for example, and they decided to scrap that all and create completely different API, using the data sets not as just blobs of data, but structured.
Any other questions? For Candy, can you name another resource manager that Spark can work with?
Yes,
Raise your hands and anybody. So another resource manager outside of Yarn that Spark works with as well. There's a popular one that's Google invented, works with Docker containers.
Kubernetes?
Kubernetes. Yes. Here, Hershey bar?
Sure.
Here you go. All right, so let's talk about the cloud. So you can run Spark and Hadoop on 3 different locations. Your local laptop or desktop, your company data center, or on the cloud. And so what do we talk about when we say cloud? We're talking about a third-party data center. So when we talk about Google Cloud or Amazon Web Services, we're talking about a data center that Google or Amazon actually host. So why cloud? The network latency time on the cloud is lower than if you were to connect servers together on your own. The data centers that Amazon or Google manages are optimized for network transfer between each of the servers. The ability to pay per use. So you can't do this on your own server. When you buy the server, you've already paid for it. But when you work on the cloud, you pay for the time that your job or your server is up. So you actually can pay for only the part of the job that runs, and then when you don't need that resource, you don't have to pay for it. And then the ability to scale horizontally in real time. This is something very unique to the cloud. You can spin up an additional X number of servers to run your job, and then spin them down to have a job complete on demand. So to kind of help talk a little bit more about the cloud and why it makes sense to transition to cloud. At Barclays, provisioning a server is a very expensive and time-consuming task. It takes, you have to have the budget set aside, and it would take months to have it set up. And you have to custom configure everything from the operating system to each of the packages, and there's a set of approval process required for it as well. At Cigna, they actually had a petabyte scale server for running Hadoop and Spark. The problem was, to justify the cost of the server, they ingested every single piece of data possible into their data lake, which kind of became problematic. I can't talk too much about that, but it became like a swamp of data. So if at the time they had AWS or Google Cloud to store their Hadoop ecosystem, it would have solved a lot of that problem. You can provision a server almost instantaneously on the cloud, and instead of paying for a petabyte of scale of data ahead of time, you only have to pay for what you actually use. So one cloud provider is Amazon Web Services, and they take more of an infrastructure as a service-based approach. To run Hadoop or Spark, you could run it on a EC2 instance, which is a rented server, and you can spin up your own Cloudera cluster. So you would basically purchase maybe 4 servers, and then install the Cloudera image on each of the servers yourself and manage it. A better solution would be to use EMR or Elastic MapReduce. They have a pre-built Hadoop image, so you can spin up a Hadoop cluster in a few minutes. Interestingly enough, you usually spin down the EMR cluster when your job finishes, but when Netflix originally spun up their Hadoop instance on the cloud, they actually had a persistent EMR cluster where they stored most of their Cloudera instance on. And then finally, sorry, not Cloudera, Hadoop instance. And finally, AWS Glue. So this is a new solution from Amazon Web Services that completely abstracts the infrastructure away. You don't have to worry about the servers, how much space is aside. It allows you to just run your Spark job and get the final results out. This is kind of a overview of the entire AWS ecosystem. To ingest data, there is Direct Connect, Snowball, Kinesis. So Direct Connect is a connection from your local data center directly into a Hadoop, specifically Hadoop VPC. You have Snowball, which allows you to transfer a large amount of data into the Hadoop ecosystem. And then Kinesis, which is a Hadoop streaming solution that allows you to stream large amounts of data into the Hadoop ecosystem. It's actually a analog to Apache Kafka. And then Firehose is just Kinesis, but with a lot less code. To store data, you have S3, which is the main distributed file system storage on Hadoop. You have Glacier, which is a cold storage system for Hadoop. RDS or Aurora. This is your managed Postgres, MySQL databases, and then AWS's own flavor of database called Aurora. DynamoDB, which is an analog to HBase, is a key value storage system on top of an AWS ecosystem. Redshift, which is a data warehouse on AWS, and Elasticsearch, which is based on Lucene, but it's a search engine that you can store data in a JSON format in. And then finally, you can analyze it using Elastic MapReduce, machine learning, which they now call SageMaker, QuickSight, which is their BI tool, Kinesis Analytics, and Athena, which is a Redshift instance that you run on the fly. There's a company called Databricks that was started by the creators of Spark. So Databricks releases a lot of open source packages out to the community because they were the initial creators of Spark that help to accelerate some of the processes, such as reading CSVs and so forth. Their main product is a user interface for running jobs, but they aren't a supplement. They don't replace the cloud ecosystem. They actually work directly with Amazon Web Services and now I believe Azure. So what happens is that your Hadoop instances your Spark jobs are run on EC2 instances on the Amazon Web Services interface, but you manage it all through their user interface. Elastic MapReduce has a very similar UI, but this Databricks UI is simpler to use and easier to manage than EMR, which is why most people go to it. Their main new offering is called Databricks Delta. And so the Databricks Delta lets you provide ACID compliance for Spark data frames. So this means that instead of having to recreate a new data set every single time, you can run an update command to update specific rows on your data frame. This hasn't been possible for the longest time, but this change here allows you to do that with Spark. Yeah. So next is Google Cloud. So Google Cloud takes a slightly different approach. They take a software as a service based approach where they kind of abstract away the infrastructure. Google is the initial inventor of HDFS, MapReduce, BigQuery when they released those papers, and the creator of Kubernetes and TensorFlow. So they're a very innovative company they're kind of leading edge on a lot of these technologies. You can run Spark on Google Data Procs, which is an analog to Elastic MapReduce on AWS. But they actually have a new solution called Google Dataflow. As a complete Spark replacement. They don't use Spark. They use a project called Apache Beam. Dataflow handles streaming and batch data essentially as the same thing. You don't have to worry about it. You just have to write the code, and it doesn't care if it's a streaming-based input set or a batch-based input set. And finally, Google BigQuery is a huge tool for them because it is an infinitely scalable SQL engine. You basically pay per query, but it scales up to petabyte-based scales. So no matter how large your query is, the performance on this thing is pretty amazing. It can actually run a petabyte-based query job and return the results back in minutes. Based on benchmarking results that we're doing at Caserta, it beat Snowflake, it beat Redshift as far as performance time. It's quite amazing. You have IBM. IBM's main play is Watson, which was started in 2007. And Watson Health, which is Watson's machine learning applied to the healthcare industry. So all the IBM-based cloud products also include Watson with it. It has an easy connection to Watson. And then also if you're using IBM products such as IBM MQ or DB2, it's an easy transition to go to IBM Cloud. Finally, Microsoft Azure. So the cool thing about Microsoft is that the environment for Microsoft is enterprise compliant. It's ISO compliant, it's SOC 2 compliant, it's HIPAA compliant. You can run Spark on Azure HD Insight. It integrates natively with other Microsoft tools. So if you're using SQL Server or Windows OS, it's a very easy transition. It has integrations with Active Directory or SharePoint. And it's very easy for enterprises to move directly to Azure if they're currently on Microsoft. To kind of go through that whole transition of the data processing, each of the cloud providers has their own tool to kind of address each of these questions. For data streaming, there's Kinesis on AWS, PubSub for GCP, IBM Event Stream for IBM, Azure has Event Grid. I'm not going to go through each of them, but you can look at the slides later if you're interested. And finally, cloud convergence. So something I'm finding is that a lot of cloud providers are actually borrowing ideas off each other. Before, Redshift was not a easily scalable system. When Amazon released Amazon Redshift, it would take hours to add additional nodes to Redshift. But then Snowflake came about, and Snowflake actually uses EC2 instances on Redshift and lets you scale horizontally at an infinite scale. So it actually performed a lot better in Redshift for processing your data. In response to that, Redshift incorporated all the features that Snowflake had into their new release of Redshift. And same with AWS Glue. AWS Glue came after Google released Dataflow as a way to kind of abstract away some of the infrastructure. So a lot of the tooling is converging as they borrow off each other to create very similar tools. And a lot of the tools are moving towards software as a service instead of infrastructure as a service, so that the developers focus more on code instead of the actual underlying infrastructure for running their jobs. I'll stop here if there are any questions.
Actually, I have a question.
Sure.
I'm pretty sure you look at a lot of things related to big data, and maybe you do participation to some migration. For example, for the same feature, you migrated from on-premise to cloud, from cloud to something else. Maybe you have some numbers or some insights about costs, from on-premise for the same solution in cloud, for example, in AWS, whatever, you reduced some amount of cost, or cost will increase. Maybe you have some experience.
Costs.
Yeah, costs.
Yeah, it really depends. It depends if you're an enterprise or a startup.
For the same functionality, the same.
But it also depends if you had a data center or not. So if you had a data center and you're moving to the cloud, sometimes it doesn't make sense for you to move to the cloud because it's cheaper to just maintain your own data center. And if you don't have a data center, generally the cloud makes more sense. But if you're an enterprise, you have different requirements such as ISO, SOC 2. So the cost for managing a cloud solution becomes a lot more because you have to always go to enterprise level of enterprise support. So it really depends on the user, but generally it's a lot cheaper to go to the cloud. But the cloud is actually not cheaper if you leave everything up 24/7. It's only cheaper if you work on demand. So if you spin everything down when you're not using it, it's a better solution. But server to server, to have your own server that you provision yourself compared to a server that you run on AWS is actually more expensive per hour. It's only cheaper because you can spin down the specific instance. So that's why having your own data center sometimes makes more sense than to move over to the cloud if you can afford it.
How about, for example, Docker solution in cloud? For example, you don't use computation resources, but you use a Docker with autoscale. I mean that you don't use native computation resources, but you're using a Docker, which can be scaled up, down, so on.
It doesn't matter if you use Docker or no Docker. Think this way. If you have your own computer, right, you can manage it, and you're doing it kind of for free. If you give it to the cloud, to somebody else, you need to pay for people who will manage that. If you're using it only 1 hour a day, as he said, then it makes sense for you to give it to somebody else, pay extra, but only to use 1 hour.
But for big solution, usually calculation is a bit different. You cannot simply tell that once someone on cloud side will be working on this, it will be more expensive, because they provide some additional benefits, additional services and so on. That's why I'm asking, because for some big solution, for some big scopes, it is sometimes difficult to get a real experience and real comparison and make decision for the future projects.
But you can think not by 1 hour, but let's say by, I don't know, 20 hours. Let's say you have a big job that runs for 20 hours. But if it runs for 20 hours once a week, or once a month, or 3 times a month, then you can calculate relatively what will be more or less expensive. If you have your website that somebody is hitting all the time, and you need to do some calculations, let's say some analytics on that data that is happening, that you need to do all the time, then obviously it will be cheaper for you to run it in your own instances.
We can talk afterwards to specific instance. We'll see whether it really makes sense. There's another question?
Just like to mention, people who have existing data centers, it doesn't necessarily make sense for them to move over to the cloud when they're already running. But is that really only the case for very large companies who already have long since set themselves up? Is it really just legacy that is not adopting cloud services?
Well, the reason a lot of legacy enterprises don't want to adopt cloud services is also because there's a bunch of compliance that goes along with it as well. And there's a fear that your data is going to be hacked if it goes to the cloud. But there's a lot of enterprises that have already shifted. Like Capital One has shifted to the cloud. There's insurance companies that are moving to the cloud. Even Cigna and Barclays are now in AWS. So it's the other thing is the data centers are not cheap to run. You have to have a facility to cool them down. So
And people to pay sellers.
and people, is even running your own servers, like managing a Hadoop cluster is not free either. So but if you can do it efficiently, if you have the scale, it does make sense to manage your own data center. But you have to be a big enough company to do that.
Even when we're hiring now, no one wants to work on like a local data, local data center. People that you're hiring have all these skills already for the cloud. So there's a lot of hidden costs, I guess you'd say, when you're managing a team that aren't necessarily apparent when you're breaking it down from, oh, I'm going to own the computer, or I'm going to rent the computer.
And then, on top of that, if you have the interfaces which are kind of compatible with both solutions, then the company can move in and out whenever they want. Like Kubernetes, for example, you can run Kubernetes on the cloud, you can run them Kubernetes on the, in on-premise, center. If your application is completely compliant, then it doesn't matter for you where you run. The company can make a decision at any point of time to move in cloud, out of cloud, to another cloud, or even go to the hybrid cloud.
Something you're saying that really resonates is that the efficiency of your platform really depends on the software engineer. When we made a big migration to the cloud, we had some teams that just didn't want to adopt and just would rent out a giant EC2 instance and just run it as if it was their local machine. Of course, that's going to be way more expensive. When you have the cloud native people using these services and applying them as intended, you can get their costs incomparably low compared to the other guys that are just saying, okay, I'm forced to go to the cloud, I'll just rent out a big computer.
I also want to make a mention, there is a company called Nutanix that lets you, if you have a data center, run your data center very similar to AWS, where it gives you a user interface to kind of pretend like you're on the cloud, but you're actually using your own data center. So there's all types of solutions, even multi-cloud solutions, where companies are using Google and Amazon Web Services together, and partial native solutions where people use their data center part-time and also have Amazon Web Services. There are every combinations of solutions that exist out there, but they're very expensive, and I don't recommend doing multi-cloud. Yeah.
So even Apple doesn't run their own data centers. If you put that on iCloud, they're actually storing it in Google Cloud. So if it doesn't make sense for Apple to run their own data centers like that, I think that really calls into question if it makes sense for a smaller company to do it. There's like a lot of economies of scale and expertise that goes into running it.
Yeah, but like, it might...
for your data, not for their own. Their own data they run on-premise.
Well, they have much less of their own data than customer data, I think.
But it also makes more sense if you have a very specialized use case. Like if you're doing high frequency training and you need specific types of GPUs that like they don't offer, then you have no choice. You need to have specialized machines. So they're a very specialized use case where you would want to have your own data center to run these jobs on as well. Yes?
Yeah, so I'm just wondering which use cases would you rather use Hadoop and which use cases for Spark?
People generally moved off Hadoop. I don't see a lot of companies using it unless it's legacy. But Spark is generally better overall. If you actually run out of memory, it'll spill into disk to process. But Hadoop is better for really, really large jobs and you have servers where you know you cannot fit in memory and you want to do a disk operation and this is going to be a job that runs for hours and hours and hours and you don't care when it finishes, and you would use Hadoop. But I see that most companies are just purely using Spark now. They're not traditionally using Hadoop. Yes?
So I have a similar question around Spark versus Apache Flink. Could you talk more about Apache Flink and I guess the future of it?
Yeah, Flink isn't gaining as much adoption as Spark is as a project. I think, so Flink tries to solve the Lambda architecture problem by handling the batch streaming with the batch loads and streaming together and kind of coordinating it. I don't know too much about Flink, but I do know that it doesn't have as much of a community adoption as Spark does, but it tries to kind of outcompete Spark. I would actually argue that Beam probably has more of a chance to survive, considering that Google is using it for data flow. And Beam is very similar to Flink. It actually handled batch and streaming together. So, yeah.
Beam is just an API. It's just like Java API. You can write programs on the Beam interface and run them in Flink and in Google platform and in Spark.
But when you run on data flow, you don't have to worry about the underlying what happens.
If you run that on Flink and it's all set up and configured, you don't have to worry about anything either. You just run it, you write it on Beam, and then you run it with Flink underneath that.
Okay, I didn't know that. So finally, the future of big data, what's going to happen? Automation of complex data processes. A lot of stuff that data engineers had to write custom code for, specifically custom code that required business logic, will start to get automated. Example includes personally identifiable information recognition. Google has an API to recognize PII data. This includes like phone numbers and social security numbers. And then AWS has an auto dedupe feature. So using SageMaker, you can actually train your data to find duplicate data sets. And I'm not talking about like data sets where every single field is exactly the same. I'm talking about data sets where like it's a duplicate but slightly off. So for instance, like John Doe versus John Doe with a period at the very end. You're going to see a lot more of these types of solutions coming out and making it easier to create data pipelines. AI-driven report development. There's a company called Telius.com, that has an automated BI solution. So with Telius, it creates the BI reports for you automatically, and you can actually ask questions to Telius in a human-readable format, such as, what was my revenue for Q3? Infrastructure is fully abstracted, movement to the software as a service model, example BigQuery. So you're going to see more and more of this where infrastructure becomes less and less of something that developers focus on. And finally, less code. So more boilerplate code gets abstracted away as more libraries get released to take that out. So that's the end. Any further questions? I'm happy to answer. Yes?
Do you see the cloud provider environment converging or dying off to a monopoly or expanding outwards?
Yeah, I get asked that question by people sometimes, especially people who want to make money off of betting on Google versus Amazon Web Services. I really don't know. I mean, so when I was at Caserta, we really pushed for Google because Google is leading edge and they're really ahead as far as the software as a service based model, but their customer service is pretty bad. Amazon has a plethora of tools that they're releasing. I mean, they're on everything now. I don't really know who will survive and what will happen. I think they're going to copy off each other, but it's a question of what happens in 10 years.
One question regarding GCP, Google Cloud. You mentioned that you're moving in that direction. As far as I know, they have a lot of issues with certifications. Because when you were talking about Azure, you mentioned HIPAA, all the stuff, and they have the certifications. Maybe Amazon had the same, but for GCP, at least they had issues with this. I don't know what.
They all offer, actually GCP, AWS all offer those certification for ISO SOC 2 and HIPAA. As far as like how comprehensive they are, I don't know. It's not applied to every service. For AWS, for instance, HIPAA compliance is only for a set of services. Yeah. So Microsoft might be way ahead in that game as far as enterprise solutions goes.
I know, like actually from Sigma, guys who are working there, they were talking about that Google Cloud maybe a few years ago mentioned that they support kind of PCI something, but as a fact they are not certified, and that's why.
It's very possible. They claim to be certified, and then they're not actually fully certified. It's their certifiable support. Like you can transition to certified. It will help you do it, but we're not actually certified. Yeah, I've seen that too. It really depends on case by case. It is per service. So some of their stuff is certified, and some of it is not certified. Yeah.
Yeah, I noticed that last year, like Google supported customer managed encryption keys on like some services.
Yeah, it's crazy. They haven't. I think it's recent release that's been out for Amazon Web Services for the longest time. Yeah, so they're playing catch up for certain things too. It's kind of ironic. It's a mishmash where like certain things are ahead by Amazon, certain things are ahead by Google. So right now, no one is kind of taking the ultimate lead. But the thing I really like about Google is BigQuery and Dataflow, and there's no other solution similar to BigQuery by any of the cloud providers out there, where you can like store and query petabytes of data and get a solution back in minutes. It just, no one else has competed for that space. Yes?
Okay, so for the, let's say the TensorFlow, Keras, or PyTorch users, let's say that they've been running this really complex model on the cloud. but then they decided they want to do distributed computing or distributed ML using Spark. What's the best way for them to kind of like implement that? For example, should they use Databricks services, or alternatively, have you heard about Horobot?
What was it called?
Horobot.
No.
Okay. So that is like a kind of a framework kind of released by Uber, and then they wanted to, that's like a framework to do distributed computing.
I don't know if the platform itself makes a huge difference per se. I mean, they're just libraries that you can import in. A Databricks definitely makes it easy to add libraries, but I'm not sure if one platform itself would be better to run PyTorch or TensorFlow with.
It's not competitive.
Yeah.
I mean, the Spark ML is very tiny subset to what others do, what other, you know, APIs or platforms do. So in your specific question,
You're talking about
there is-
ML,
yes. Well, MLlib is a part of Spark offering. If you run in TensorFlow or PyTorch or whatever, there's no adequate comparable stuff in MLlib. MLlib is very, you know, it's very basic. It's MLlib is some attempt to distribute, to run distributed processing on subset of scikit-learn.
Yeah.
Subset of scikit-learn. Now you're talking about completely different level.
Yeah.
You know, so there's no move. If you are on TensorFlow, you will be on TensorFlow. You cannot move anywhere.
So we're going to end the Q&A session, but I'll be here if you guys want to ask any more further questions. So thank you everybody for... I also have 4 candy bars left, since some of you guys killed my questions. So if anybody wants candy, happy to give it away. Thanks.